Okay, so today we're going to venture finally into chapter 4, which is on the principle of mathematical induction, an extremely important and central technique in mathematics, which is sort of covered both in sections 4.1 and 4.2. But before we do that, I'd like just to finish up one thing about the division theorem. But first, back to the division theorem. So let me just restate the division theorem for you. You can, of course, just look at it in your notes, but it's worth restating. So for all integers a, b, with b positive, because I'm going to divide by b in a second, there exist unique integers q and r such that a is equal to bq plus r. Okay, right now, as I've stated it, remember this is not true because there's lots of ways to write a as bq plus r, but there's a unique way if you impose that the remainder is positive or non-negative and less than b. Right, so this just says that you can always divide a by b and get a unique quotient as long as you impose that the remainder is small enough. So that's the division theorem, but let me just make an observation. Let's let b equal 2. If we let b equals 2, what does this say? This says that for every integer a, for every a in z, there exists a unique q and r in z such that a is equal to 2q plus r, where r is between 0 and 2. In other words, r is 0 or 1. Right, so r equals 0 or 1. So what is this saying? This is saying that every integer a can be written either as 2q or 2q plus 1. In other words, this is saying every integer is either even or odd. Every integer is either even or odd. And I guess, but not both, right? Because the q and the r are unique. There's only one way to do this. So once we prove the division theorem, we'll also get that theorem for free. Okay, another way to say this, though, or another way to say this is that every integer is a either has a minus r equals 2q, sorry, a minus 0 equals 2q, or a minus 1 equals 2q for some integer q. Which means what? That either a is congruent to 0 mod 2 or a is congruent to 1 mod 2, which remember we said is this is the same thing as saying that a is either even or odd. So with this view of the situation, there's a nice corollary of this theorem, which works for any modulus n. So for all integers with b greater than 0, there exists a unique integer r with 0 less than or equal to r less than b, such that a is congruent to r modulo b. All right, this says that when you consider integers modulo b, let's say b is 9, right? If I go mod 9, then every single integer is either congruent to 0, 1, 2, 3, 4, 5, 6, 7, or 8. So those 9 numbers, 0 through 8, represent all of the possible integers if you only care modulo 9. Okay, so why? So this is because if a equals bq plus r, then a minus r equals bq. So a is congruent to r mod b. Right, so the theorem says that for any a and any b, I can always find a unique r between 0 and b such that a is congruent to r mod b. So this is really just another way to state the theorem where you just translate between this and this because these mean the same thing, basically. This is an extremely useful fact, okay? Useful. Because one thing this lets you do is it lets you break into a finite number of cases. If you only care modulo n. Right, so if you want to prove something about all possible integers modulo 9, you only need to check 9 things, 0, 1, 2, 3, 4, 5, 6, 7, 8, because every integer is equivalent or congruent to one of those modulo 9. So let me give you a good example of this theorem. So for every integer n cubed is congruent to n mod 3. And this is maybe not an obvious fact. I bet if I asked you this at the beginning of the quarter, you wouldn't know. I mean, I guess you maybe wouldn't have known what modulo 3 was, but I could say take any number, cube it, divide both answers by 3, see your remainder, then they're always the same. How do you prove something like this? Well, we need to prove something for every possible integer. But since we only care about the result modulo 3, this suggests that maybe we can do it by cases. So here's the proof. So I'm trying to prove something is true for every integer n, so let's let n be an integer. According to the corollary above, there are 3 cases. Modulo 3, there's only 3 cases. Let's call them case 1, case 2, and case 3, and label them clearly so our reader knows what we're doing. So case 1 will be n is congruent to 0 mod 3. Case 2 will be n is congruent to 1 mod 3. Case 3 will be n is congruent to 2 mod 3. Maybe I should make these cases 1, 2, and 0, but we've come too far. Right, but now it's clear that every possible situation is covered here by the previous theorem. So these cases really do cover everything. Okay, well, if n is congruent to 0 mod 3, then by this theorem on modular arithmetic says that if n, right, you imagine an n here, if n here is congruent to 0, then when you cube n, you get n cubed is congruent to 0 cubed. That's what it's saying, right? If n is congruent to 0, then n cubed is congruent to 0 cubed. Right, this theorem says that you can do arithmetic on either side of a congruent sign modulo n. So then by a theorem from last time, which I'll label in your notes, of course, n cubed is congruent to 0 cubed mod 3. So n cubed is congruent to 0. 0 cubed is just 0, which is congruent to n, because I assumed that n was congruent to 0 mod 3, which is what we wanted. Similarly, if n is congruent to 1 mod 3, then n cubed is congruent to 1 cubed is congruent to 1 mod 3. Sorry, which is congruent to n again, because n is congruent to 1. And similarly, if n is congruent to 2, then n cubed is congruent to 2 cubed, which is congruent to 8. But 8 is congruent to 2 modulo 3, which is congruent to n. So in every possible case, you get that n cubed is congruent to n. Hence, this result is true. This non-obvious result is true. Okay, so, I mean, this is just an important consequence of the division theorem. If you're working modulo 12, every integer takes on one of 12 values modulo 12. But now back to the principle of mathematical induction. Okay, this is a really powerful technique. Okay, and what it does is it allows you to prove statements for every integer. Okay, so let's go back. This is a good motivating theorem. This theorem is about every possible integer, right? Which seemed a little bit daunting at first, but then we could just reduce to cases, so there are really only finitely many things to check. But sometimes you want to prove something that's really truly about an infinite number of integers or an infinite number of things, whatever those things are. And if you want to prove something about infinitely many things, that seems kind of tricky, right? Because you only have finitely much time. You only have a finite amount of ink. How can you prove something about infinitely many things at once? So this is one powerful technique that allows you to prove things about the integers. It's not the only one, but it's one very powerful technique. So let's talk about the technique first. Let's talk about sort of why it works. And then let's see some examples. Okay, so this technique is called the principle of mathematical induction. Okay, so this is a technique. So you can either call it the principle of mathematical induction, or you can call it mathematical induction, or you sometimes might just call it induction. So in future classes, or in this class, you might say by induction when you mean by the principle of mathematical induction. Okay, so this is a technique used to prove a statement P of n. Okay, so I said for all integers, but when we introduce it, I'll say for all natural numbers n. So if you want to prove a statement for that is true for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for every natural number, one thing to try is mathematical induction. Okay, so a proof by induction is structured as follows. Okay, so there's two steps to a proof by induction. One is called the base case, and one is called the inductive step, which you should try to clearly label in your proofs. What's the base case? In the base case, you just prove P of 0 is true. So you just prove a single case. So this you can oftentimes do very concretely by some sort of computation. Okay, in the inductive step, you do something a little bit trickier. You prove that for all natural numbers k, the conditional statement, if P of k, then P of k plus 1 is true. Okay, this is the technique called mathematical induction. If you want to prove a statement about every natural number, you get to prove, you can prove it by proving just two things. Proving that, right? So in other words, right, what I'm saying is here, what you want to prove is you want to prove that P of 0 is true, and P of 1 is true, and P of 2 is true, and P of 3 is true. You want to prove that all of these things are true. But what the principle of mathematical induction lets you do is it lets you just prove two things. First, you prove that P of 0 is true manually by hand. So you prove that P of 0 is true. That's the base case. And then in the inductive step, you prove a conditional statement. You prove that if P of k is true, then P of k plus 1 is true. So in this step, you're proving a conditional. Right? I'm not proving P of k plus 1. I'm proving if P of k is true, then P of k plus 1 is true. So in this step, I can assume P of k and use it to deduce P of k plus 1. Right? So why is it enough just to prove these two things? Why does that prove it for all natural numbers? Well, in the base case, you prove that P of 0 is true. But then in the inductive step, you prove that as long as P of k is true, then P of k plus 1 is true. So since I checked that P of 0 is true, that means that P of 0 plus 1 is true. So P of 0 implies P of 1. So now you know that P of 1 is true. But again, in the inductive step, you prove that for every natural number k, if P of k is true, then P of k plus 1 is true. So once you know that P of 1 is true, you prove, if P of 1 is true, then P of 2 is true. And once you know P of 2 is true, P of 3 is true. Once you know P of 3 is true, P of 4 is true. And so you eventually prove P of n is true for all n, etc. Right, so the principal mathematical induction is actually a thing that we're assuming. This is an axiom of modern mathematics, which is if you prove a base case and an inductive step, then it implies that it's true for every natural number. Okay, so one thing that you can do is you can try to visualize. So we can visualize this. Technique as imagining each case as a domino. Imagining P of 0, P of 1, P of 2 are dominoes. And then visualize P of k is true as the kth domino falling over. Right, so at the beginning, you have an infinite list of statements that you're not sure whether they're true or not. You're trying to prove it. P of 0, P of 1, P of 2, we have an infinite number of dominoes. And we'll say that it's true if it falls over. Well, in the inductive step, what you're proving is that if the kth domino falls over, then the k plus first domino also falls over. So in the inductive step, you're proving that one domino knocks over the next domino. So I have a bunch of dominoes, and I've just proven that if the kth domino falls, then the k plus first domino falls. And then the base case is like pushing over that first domino. So I've lined up all my dominoes. I prove that each one pushes over the next domino. And then I push over the first domino. That means all the dominoes will eventually fall over. Okay, another visualization technique people have is like you're climbing up the rungs of a ladder. So in the inductive step, it's like you're proving that if you can get to the kth step, then you can get to the k plus first step. And then in the base case, you're putting your first foot on the first step of the ladder. So if it's possible to go from the kth step to the k first step, and you can get to the 0th step, that means that you can get to every step on the ladder. Okay, so this is the technique. It's a little bit abstract, obviously. I haven't actually said anything concrete here. I haven't said any concrete statement for P, for example. We'll see examples in a second. But one note here is that it's the way that I stated it was I stated it as if you want to prove a statement for all natural numbers, but it's a little bit more flexible than this. So note that the base case need not be 0. So if you're asked to prove something like, oh, for all natural numbers n greater than or equal to 1, something is true, then what you can do is you can prove in your base case that p of 1 is true, and in your inductive step that if p of k is true, then p of k plus 1 is true for all natural numbers k greater than or equal to 1. Because if p of 1 is true, then p of 2 is true, then p of 3 is true, then p of 4 is true. And so this is like I'm pushing over the dominoes starting from 1 rather than starting from 0. So really you could start anywhere here, right? So if you wanted to prove something was true for all natural numbers greater than 17 or something, you can prove that p of 17 is true and prove that p of k implies p of k plus 1 for every k greater than or equal to 17. So in principle, you can start at any natural number you want. Most commonly, though, you start with, the kinds of statements that I'll ask you to prove most commonly start at 0 or 1, occasionally 2, occasionally 3. It's of course possible to cook up statements that are true from 17 onwards, but not from 16 smaller. It's not so hard to do, but those are a little bit, the best ones that I can think of are artificial anyway. Okay, now the only real way to learn mathematical induction is to do a bunch of proofs using mathematical induction, and then you'll become very comfortable with it, I promise. It happens to every mathematics major. But before you can prove anything by mathematical induction, first you need to see some proofs by mathematical induction. Okay, so I'm going to give you the most classic proof in the world. If you Google mathematical induction, probably every single site that tries to teach you mathematical induction will use this as their first example. So here's the statement. For all natural numbers n, let's say n greater than or equal to 1, the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. The most classical statement that's ever proved by induction. Okay, so first of all, a hint that you might need to use induction is if you're asked to prove something like for all natural numbers or for all natural numbers starting from a certain point, this should set off some alarm bells like, oh, maybe I can try induction. Because there's an infinite number of things to prove, right? Another like telltale sign that you want to use induction, or that when you're trying to write a proof and you're trying an induction, another telltale sign is if like the 10th case helps tell you about the 11th case. Because of that inductive step, you're allowed to assume the kth case to prove the k plus first case. So if you're asked to prove a statement about all natural numbers n, and one case seems to tell you something about the next case, that's also a good sign that induction is something to try here. And this situation is like that, right? Because if you know something about the sum of the numbers from 1 to 10, then you know something about the sum of the numbers from 1 to 11, right? The sum of the numbers from 1 to 11 is just 11 more. So I would say everything about this very classical setup really suggests that you should use induction here. So let me try to prove this using induction. I'll try to write this one as cleanly as possible. So you should tell your reader, we will prove this by induction. You have to tell your reader what you're doing, always. Now, the principle of mathematical induction says, I just need to first prove the first case, in this case, p of 1. And then I just need to prove that if P of k is true, then P of k plus 1 is true. Right, so the statement here, I should say, this statement is the statement P of n. Because as you plug in different values for n, you get different statements, right? So we'll prove this by induction. What's the base case? So we want to prove P of 1, right? So we want to prove the sum from I equals 1 to 1 of I equals 1 times 1 plus 1 over 2. This is what we need to prove in the base case. But this is sort of trivial. The first one is you just add up a single 1. The second one is 1 times 2 over 2. So both sides are equal to 1. So the base case holds. So the base case is always really easy, or not always, but often very easy. You're trying to prove something for all natural numbers n, but you get to just check one case. And one case, oftentimes you can just plug in and then see that it's true, right? So it's no surprise that this formula is true if you let n equals 1. Now what's the inductive step? So the inductive step, what you're trying to prove is you're trying to prove P of k implies P of k plus 1. So let me put this in blue. So we want to prove here, right? This won't be part of my final proof, but this is just in blue. P of k implies P of k plus 1 for all k greater than or equal to 1. Right? I want to prove that P of 1 implies P of 2, P of 2 implies P of 3, P of 3 implies P of 4. That way all the dominoes will fall down. And what is P of k? P of k is the statement the sum from I equals 1 to k of I equals k times k plus 1 over 2. The statement P of k plus 1 is the sum from I equals k plus 1, I equals 1 to k plus 1 of I is equal to, I should have just put it here, is k plus 1 times k plus 1 plus 1 over 2. And again, this statement seems ripe for induction because the difference between this and this is very small. Those are the same expression except just with an additional k plus 1. So I want to prove P of k implies P of k plus 1. That's a conditional, which means that I'm allowed to assume that P of k is true for some k. So assume that for some k greater than or equal to 1, that the sum of from I equals 1 to k of I equals k times k plus 1 over 2. So I get to assume P of k. This assumption is called the inductive hypothesis. It has a name. It's in the inductive step. You have to prove a conditional. Which means that you get to assume the hypothesis and try to prove the conclusion. So when you assume that P of k is true, that's called the induction hypothesis. So it gives you something to work with in the inductive step. Okay, we wish to prove that the sum from I equals 1 to k plus 1 of I equals k plus 1 times k plus 2 over 2. If I can prove this, then I'll have proved P of k implies P of k plus 1. But now note that the sum from I equals 1 to k plus 1 of I want to show that this is equal to the right-hand side. That this is equal to just the sum from I equals 1 to k of I plus k plus 1. This is just summation notation. If I add up all the integers from 1 to k plus 1, it's like adding up all the integers from 1 to k plus k plus 1. And now, by the inductive hypothesis, I know what this is. I get to assume that this is k times k plus 1 over 2. So here, I'm using the inductive hypothesis. Okay, but now this is just an exercise in simplifying some fractions. This is k times k plus 1 plus 2 times k plus 1 over 2. I just got a common denominator. And now I can factor the numerator to k plus 2 times k plus 1 over 2, which is what we wanted. Right? So I've proven what I wanted. Now I've proven the base case. I've proven the inductive step. So by the principle of mathematical induction, I've proven this statement for all natural numbers n. So here I'm invoking the principle of mathematical induction, which says that this technique works. So hence, by induction, the sum I equals 1 to n of I equals n times n plus 1 over 2 for all n greater than or equal to 1. Okay. Yeah, so like I said, this is your first inductive proof. This is the first time, I mean, maybe, that you're seeing the principle of mathematical induction. So if you are a bit confused, that's natural. That's normal. Everybody's a bit confused the first time they see induction. If you're not confused, even better. But we will have lots of practice proving things by induction. And as you do more and more proofs, you'll get more and more used to it. And then you'll begin to understand the technique more and more. So in fact, let's do the next one. Here's the theorem for all natural numbers n greater than or equal to 1. The sum from I equals 1 to n of 2i minus 1 equals n squared. Okay, I promise that the technique can be used to prove things other than just summations. The thing is, summations are so ripe for the picking for mathematical induction because the kth case tells you quite a bit about the k plus first case, as we saw previously, right? Compare the kth statement to the k plus first statement. They differ by just a very simple thing. So because of this, things like this scream induction. Right? Just like when you took calculus, there were certain kinds of sequences that like screamed ratio test, right? Like you learned how to recognize things that like, oh, that's definitely a ratio test. In exactly the same way, there are certain things that you'll need to prove in mathematics in future classes that was like, oh yeah, that's got to be induction. It just looks so ripe for the picking for induction. Oh, one thing I forgot to mention about this theorem is that maybe you recognize this theorem being maybe an apocryphal story about Carl Friedrich Gauss. Hopefully you've heard this story. I'm sure many of you have, but you know, as your intro to proof professor, it's somewhat my responsibility to make sure that you understand all the standard mathematical folklore. And it's good because I actually enjoy doing it anyway. So Carl Friedrich Gauss, one of the greatest mathematicians of all time, made humongous contributions to many, many areas and was definitely a genius. But the story goes, supposedly, that in like, I don't know, the 3rd grade or something, he had a school teacher who was tired one day, right? And so for the math lesson said, you know, I want you to add up all the numbers from 1 to 1,000. And so right, I want you to add up 1 plus 2 plus 3 plus 4 plus 1,000, thinking that this would take third graders a really long time, right? So that the teacher can have some peace and quiet, something that we all long for, all of us who have students. And then Gauss came up with the answer in like 30 seconds, right? So what did Gauss do? Supposedly, he noticed that you can break this sum up into a bunch of pairs, right? So what you can do is you can take 1 plus 2 plus up to 500. Let me say, yeah, 500. And then you can go plus 501, 502, 999, 1,000. Okay, so instead of adding up all the numbers from 1 to 1,000, you can add up all the numbers from 1 to 500 and then all the numbers from 501 to 1,000. Right, and what Gauss noticed is that these numbers sum up to 1,000, these numbers sum up to 1,000, sorry, 1,001. All these numbers sum up to 1,001. And how many are there? There are 500 pairs of 1,001. Right, so this is 1,001, this is 1,001, this is 1,001. And there's one up to 500, so there's 500 of these. So this formula is 500 times 1,001. Right, which is, incidentally, 1,000 times 1,001 divided by 2. So to add up all the numbers from 1 to n, you can sort of break them up into n over 2 pairs, where each of the pairs sums to n plus 1. So their total sum is n times n plus 1 over 2. It's, of course, a little bit different if n is odd, right? Then you have like a hanger-oner at the end, right? That doesn't match up with anything. But this formula basically holds. So this is basically the formula that Gauss derived, supposedly as like an 8-year-old. Right? And this is also a very nice proof of this fact, right? The only thing is that your proof would need to be slightly different for odd and even n, whereas the inductive proof is more uniform, right? Here, it doesn't matter if n is even, it doesn't matter if n is odd. Whereas this clever Gauss trick does depend on that. On the other hand, it just seems so much more clever. So I don't know if the story is true or not. Definitely Gauss was probably smart enough to do this, but maybe this was an urban legend even back when Gauss was a little kid, or before Gauss, and then after Gauss, because he was such a famous, great mathematician, it got attributed to him. I'm not sure. Anyway, so this is one of the formulas that you should just have memorized, basically. You should also, I guess, know the sum of the squares. It's like n times n plus 1 times 2n plus 1 over 6, which I guess I'll probably assign as a homework because it's a Morgan induction practice. But that's a mathematical folklore that you should just know. Okay. Back to this, though, away from my tangent. Again, the only way to learn how to prove something by induction is just to do a bunch of induction proofs. So here's induction proof number 2. We'll notice that this is asking us to prove something for all natural numbers n greater than or equal to 1 and involves some sort of summation. So this suggests that an induction proof would be fruitful here. So we prove this by induction. Always tell your reader what you're doing. Right, so the base case. So for the case n equals 1, we want to show the sum from I equals 1 to 1 of 2i minus 1 equals 1 squared. But again, the left-hand side only has one summand. It's 2 times 1 minus 1, so it's 1. The right-hand side is 1. So both sides equal 1, which verifies the base case. Right, so, I mean, you can see the power of induction, right? I'm trying to prove some highly non-obvious formula for every natural number. In order to do it, I can just check one almost trivial case. And then in the inductive step, I need to prove something kind of tricky. I need to prove a conditional. But in proving a conditional, I get to assume a whole lot. I get to assume the inductive hypothesis. I get to assume that it's true for some k. And then with that huge assumption, I just need to prove that it's true then for k plus 1. It's true for the next case. So inductive step. Now assume that for some k greater than or equal to 1, that p of k is true. What is p of k? It's the statement I equals 1 to k of 2i minus 1 equals k squared. We want to prove the k plus first case. So the sum I equals 1 to k plus 1 of 2i minus 1 equals k plus 1 squared. This is what I would like to prove. Okay, now observe that I equals 1 to k plus 1 of 2i minus 1 is, again, the first sum plus the last term. So this is, I can add up the first k terms, and then I can add the k plus first term. What is the k plus first term? It's 2 times k plus 1 minus 1. That's the k plus first term. So all I've done is I've just broken the sum up into the sum of the first k and then the last thing on the list. Okay, but now I get to assume by the inductive hypothesis. So here's where I'm using the inductive hypothesis. I'm assuming the kth case. So this first sum is just k squared. And then I get 2k plus 2 minus 1, which is k squared plus 2k plus 1, which is k plus 1 squared. So by induction, for all natural numbers n greater than or equal to 1, this formula holds. This is a non-obvious formula, but it's true. Okay, by the way, what does this formula say? This formula says that if you add up the first n odd numbers, you get n squared. Right, that's really what the sum is. Right, the sum is 1 plus 3 plus 5 plus the nth odd number equals n squared, which I think is not obvious. You should play around with it. You may come up with a geometric proof. There's many other proofs, but this proof by induction says that this formula does work. Okay, so let me make some comments on this. Induction is a really, really powerful technique. On the other hand, I would say that sometimes the proofs can be kind of non-illuminating. So in some sense, this proof doesn't show you why this formula is true. It just shows you that it is true. And another thing is that in order to prove this, we need to know what the formula was to begin with. Right? So that's kind of a drawback. If I just asked you, what is the sum of the first n odd numbers? You would need to figure out what you thought the answer was first before you could prove it by induction. Right? I mean, maybe the better example is this previous one, this proof of the first n natural numbers being n times n plus 1 over 2. The proof by induction works. It's great. But actually, this thing that I put in the corner in blue and red, this Gauss proof, or apocryphally Gauss's proof, actually seems more illuminating. Right? It seems like this helps you understand more what's going on. So a proof by induction is very powerful, but can sometimes be not so illuminating. And another drawback is that you need to know the answer before you can start to prove it. So like, how do you generate a formula like this? Again, you should try to play around with it and see if you can maybe get a geometric proof or something, right? Another last comment I have before I'll let you go. I mean, we'll of course do more proofs by induction next time, is something, this k here versus n. So in your inductive step, so it's like the n somehow is like a global variable that's supposed to represent any natural number that you want. So I'm trying to prove for every natural number n, this formula holds. In the inductive step, it's like I'm choosing a particular k and saying if k holds, or if the kth case holds, then the k plus first case holds. So it is always actually best practice to not use the same variable here, this k, as you used here, the n, because they're playing different roles in the proof. The n is like every natural number n. The k is like, I'm going to focus on a specific k, assume that it's true for that specific k, and then prove that it's true for the specific k plus 1. Okay, so this is a common, I mean, it's sort of just a best practices thing. It doesn't, what I'm trying to say is many students will put an n here instead of a k, and it's okay. It's just, to my taste, it's not quite as clean, but that's okay. I would just strive to, the clearer you learn it, the better. So I would strive to remember to use a different variable name there. And then in this class, you should write out your proofs by induction extremely carefully, because this is where you're learning it. In future math classes in an undergraduate, you can maybe be a little bit looser. You maybe don't need to say as many words in the inductive step, right? But you still need to do a base case and inductive step. Then when you're a graduate student, you're allowed to say even less. You can be even a little bit sloppier. And then by the time you're a mathematician, a math professor, right, in some of my papers, the proof just says this follows from induction, because it's sort of understood that everybody reading it will know how to do the induction. But in this class, you want to write your proofs as cleanly, as carefully as possible. So that's what I am asking you to do. Okay, so next time we'll see more proofs by induction. You'll of course have many homework problems involving proofs by induction. So hopefully you can get comfortable with them pretty quick.